We're next going to talk about yet another scheduler operator that's used in conjunction with the observable class. It's not really in the observable class. It's more used in conjunction with the observable class. And this operator is Schedulers.computation. And in general, the scheduler operators are used to run other operators in designated threads or thread pools. Schedulers.computation is designed to run something in a CPU-bound thread pool that's pre-created for you when the program starts up. So what does this operator do? It's actually quite simple. As you can see, it's called computation. It's a factory method, and it hosts a fixed size pool of single-threaded executor service-based workers. So it's a pool of threads. That's the best way to think about it. And the computation factor method returns a new scheduler that is designed to work for parallel computations. And it's designed to work for particular types of parallel computations. It's not designed to work for just any old type of computation. It's particularly designed for fast, runnable, non-blocking executions, things that are not going to block, like a computation-bound job. And it's important to remember here, blocking really means I/O blocking, not sitting there in a loop, spinning, doing computations. That's sort of blocking too, but that's not the kind of blocking we're thinking of here. And I think the other key thing is fast. You don't want it to be running for a long time. So it is not designed to be used for I/O-intensive operations. It's designed to be used for computation or CPU-bound computations, as opposed to I/O-bound computations. Here's an example of how this can be used. This is just looking at the example we looked at on the previous lesson in a little bit more detail, focusing more on the thread pool part. So remember, we've got ourselves a stream of big fractions we got using the observable from iterable factor method, and we're going to use the flat map concurrency idiom to do all the multiplications of things, and it's going to use the scheduler's computation thread pool. And what that means is for each of these big fractions that comes in, those big fractions will be doled out to threads in the scheduler's computation thread pool. And therefore, assuming we have more than one core on our computer, those computations will in fact run in parallel, which is exactly what we want to get. Now, thing to remember, from callable is lazy. So that means that the multiply method here actually runs in the computation thread pool, not in some other context. It runs in the computation thread pool, even though observable from callable appears before the call to subscribe on. This is one of those kind of interesting, quirky, fascinating semantic issues of both RxJava and the Project Reactor mechanisms for concurrency. So because this is lazy, it'll run the multiplication in that context. If we replaced observable from callable with observable just, then it wouldn't run, this call would not run in the computation thread pool. It would run in the so-called assembly thread, basically the thread in which it was created, which is not what we want here. We want that multiplication to take place in the pool. Now, if you were somehow just absolutely adamant about using just here, which you should not be, but if you were, you could say observable.just, and then you could simply omit the big fraction, put a subscribe on, and then put a map call after subscribe on, which would then get the same behavior. But this is more concise, and once you understand the lazy semantics of from callable, I think it's more intuitive to understand. And then notice that the last thing we do here is after all those computations finish, the final thread that finishes the final computation in that pool will be used to call the reduce operator. We'll talk about reduce here in just a moment. And reduce, as reduce does in Java streams, is going to take the results of these things and it'll go ahead and add everything together to get a final reduced result, which is adding up all the multiplied values together. Now, internally, the computation thread pool, the threads in the computation thread pool are implemented as so-called daemon threads. And we haven't talked a lot about daemon threads. You can learn more about daemon threads here at this link, but the quick Cliff Notes discussion of daemon threads is if there are no more non-daemon threads left, then the daemon threads automatically shut down, thereby ensuring that you don't delay the shutdown of a program just because they're daemon threads that are working. However, this, of course, has the important property that you can't start a bunch of computations running in the computation thread pool in parallel and then have, say, the main thread exit, because all those other threads are going to shut down. And that's precisely why we use things like the async task barrier to make sure that we don't exit the main thread while the other threads are running around in the background. Project Reactor has a method, factor method called parallel that works in a similar way to the computation factor method in the schedulers class in RxJava. And the Java common fork join pool is also very similar as well. The main difference, of course, is that the common fork join pool can be adapted to work with I/O-bound tasks by using the managed blocker mechanism, whereas parallel and computation are really designed to be used only for non-I/O-bound operations, CPU-intensive, CPU-bound, computation-bound, and so on and so forth. So common fork join pool is a bit more flexible because you can make it spawn more threads to work with I/O-bound tasks. Okay, so that's the end of the discussion of the scheduler operator in the observable class.